Hi everyone! This is section 15.8 on triple integrals in spherical coordinates. I know recently it probably seems like I'm really running this triple integrals thing into the ground. We've been doing these a lot and in lots of different coordinate systems. I promise this is going to be the last of the sections that we're doing on triple integrals. We're going to move on to new kinds of integrals and different techniques for evaluating those from here. But before we jump off to this brand new shiny stuff, this is the last of the coordinate systems we're going to have to do for triple integrals. Now, refresher on where we're at so far. The coordinate systems that we have for 3 dimensions are Cartesian. These are going to be the standard coordinate system that we've got whenever I give you an x, y, z coordinate. So basically these, if I get my pointer straight here. These are going to be my x, y, z style coordinates for this point. X obviously represents how far out I go in the x direction. Y represents how far out I go in the y. Z represents how far out I go in the z to get to my point. Last time we introduced cylindrical coordinates. Cylindrical coordinates, here you kind of use something a little bit similar to polar for your x and y. Instead of specifying x and y using distance in the x direction and in the y direction, we use an r and a theta. Meanwhile, we keep our z the same. The way that this worked is basically if you think about the shadow, okay, that your point would cast on the xy plane, and if you think about connecting that point over to the origin, well, the distance from that shadow point to the origin, this is what I'm using as my r here. And then the theta is just going to be the angle off of the positive x-axis towards that line segment that we just drew between the shadow point and the origin. Okay, so that's kind of what's going on with our x and y. Another way to view this is if you just totally ignored the z component here and you just looked at the xy plane, your r and your theta look like your polar coordinates in the xy plane. And then the z, we didn't do anything with the z. Z just stays as is. Okay, now the motivation for these guys, this is pretty much our default coordinate system, okay, that we pretty much start most of our problems in. You know, especially if you have rectangular regions, you definitely want to be using Cartesian. Okay, that's probably where we have as a starting point. On the other hand, we mentioned that cylindrical, this guy is good for round regions, or at least some kinds of round regions. What I wanted to look at today is, well, we've noted that cylindrical helps us when my sides are round, you know, and your top and your bottom might not necessarily be. You know, we did leave our z coordinate completely alone. We didn't touch that guy. Today I want to introduce a coordinate system for regions that are maybe a little bit rounder than that. Okay, so if I have volumes that I'm integrating over that deal with things like spheres and cones, maybe instead of cylinders, hopefully this makes sense, use cylindrical for cylindrical regions, spherical for spherical regions. If our regions are especially round, we maybe might want to consider this alternate coordinate system. Now, how does this coordinate system work? Well, let's go ahead and get going here. The coordinate system that I'm going to introduce to you, we will detail the locations of points in terms of rho, theta, and phi. Okay, so this very first character over here, this, I'm not reading it as a p, I'm meaning for this to be the Greek character rho, and theta and phi. Side note, some people will draw their phis in the alternate notation here. I don't really care which way you draw it. They mean basically about the same thing. But at any rate, rho, theta, and phi, these are going to be our coordinates that we are discussing here. How the heck do I get these back? Well, rho, first off, you notice when we broke down cylindrical coordinates, that r was actually kind of a weird distance to measure. You know, I had you guys figure out what our sort of, you know, shadow point would have been. okay, down on the XY plane, and then we drew a connecting line between that shadow point and the origin. I'm not going to fiddle with any of that, okay? What I'm going to do right now for spherical coordinates is I'm going to take whatever the heck this point is, and I'm just going to figure out a straight line distance directly from that point to the origin, okay? So that straight line distance there, this guy is what I am measuring as rho, okay? So I'll go ahead and make that note. This guy is my distance from my point to the origin, okay? Theta, what about theta? Well, this one's actually not new, okay? If you think about connecting that shadow point to the origin via some sort of a line segment, and then you measure the angle from the positive x-axis towards that segment, this is the exact same theta that we did before, right? So this theta, this is basically the same exact theta that we used in cylindrical. Now this last coordinate, here you'll notice that I had drawn this line from my point in question to the origin, and that gave me this line segment. Well, what I'm going to go ahead and do now is think about the angle from the positive z-axis towards that line segment, okay? That guy is going to give me my phi, okay? So here I'll go ahead and, you know, add in a little extra detail here. What I'm going to do is draw a segment, okay, from my point to the origin, okay, and then I'm going to go ahead and measure the angle between that segment and the positive z-axis. Okay, so this is where each of my variables in this coordinate system is coming from, okay? Now, a comment, in case you're a person that, you know, pulls notes from multiple sources, or maybe you're taking some physics classes right now where you're also dealing with stuff in spherical coordinates, I will give you a warning for using outside references whenever you are dealing with problems related to spherical coordinates in this class. Different disciplines may change the labeling and the ordering of these things that I am calling rho, theta, and phi. First off, rho, this distance to the origin from your point. Some texts may use r instead of rho, so that thing that we called r in cylindrical, that's a totally different distance. You're going to want to pay attention to context in your outside source to figure out what they really mean by rho or what they mean by r. And then this is also kind of confusing. What we call theta and what we call phi, the physicists do backwards, and some other disciplines also do backwards, okay? So be careful if you're trying to use outside sources. Make sure that you know which of these points we're referring to whenever we do these conversions, okay? Just make sure that you don't get tripped up doing that. Now, with that said, let's just make sure that we got the feel for this. I'm going to go ahead and give us a Cartesian point to play around with here, okay? 0, 1, 1, since it's Cartesian, this is supposed to be x, y, and z here. That means that I go out 0 units in the x direction, and 1 unit in the y direction, and 1 unit in the z direction. So if I wanted to, it's maybe a little bit crooked here, if I wanted to figure out where my point was, we're in the YZ plane. We're right there. Now, if I want to write this in spherical coordinates, well, one thing that I can think about is, you know, we said that we wanted rho and theta and phi here. My rho was supposed to be my distance from this point to the origin. Now, if I think about just kind of what's going on here in a two-dimensional sense, you know, if I just have the y and z axes here, hopefully, you know, we can worry about this straight line distance from that point to the origin. Yeah, you can kind of Pythagorean theorem this out or distance formula this out. I can view there as being a right triangle here with two legs of length 1. If you use Pythagorean theorem to figure out the distance to the origin, should be the square root of 1 squared plus 1 squared. You're basically going to get root 2 as the length for this side. For my theta, okay, again, if you think about where your shadow point is for this particular point, draw a line between that point and the origin, and then worry about the angle between that segment and the positive x-axis. Well, in this case, we cover, basically this one quadrant in the xy plane, so that angle should be 90 degrees, or usually use radians for each of these coordinates. This should be pi over 2. Phi, on the other hand, I've mentioned that if you think about drawing a straight line segment from your point to the origin, you are worried about the angle in between the positive z-axis and that line segment. Now, on this YZ plane thing that I've just drawn, that's basically this angle right here. You notice that this line segment is basically the line y equals x. That's pretty much symmetric in the first quadrant. So that angle that I've established right here, this should be 45 degrees, or I should also be able to use pi over 4 here. Okay, so my spherical point, the order that we usually give things in math, is rho theta phi. That means that I want this to be root 2, pi over 2, and pi over 4. Okay? Now, with that out of the way, a question that I can ask, I've got this coordinate system here that I can do these points in. Why would I give you the coordinate system? Well, kind of like what we did before in changing things over to spherical, one of the nice things about, cylindrical with our rounded regions is that sometimes if we looked at our region that we would have to integrate over, whatever that volume is, in that coordinate system, maybe it could be expressed in intervals instead of weird functions, right? Like for cylindrical, you could express a cylinder totally in terms of constant bounds without having to use any weird square roots or anything like that. Now, here, if we wanted to do the same thing, we want to get a feel for what constant functions look like so we can figure out how to set up our intervals, okay? Now, for example, here, if I set rho equal to k, okay, so I'm making the assumption k is supposed to be a constant here. If I make that assumption, what does this surface look like? Well, rho is supposed to be some sort of a distance from the origin, okay? So here, if I specify some sort of positive value for k, that's a positive distance from the origin, you're basically saying you can go out in any direction k units. And if you're going out in any direction k units, well, you're basically giving yourself a sphere of radius k, right? So here I'll go ahead and note we're typically going to get a sphere of radius k. Technically, if you end up with a negative value for k here, we're going to kind of play by the same rules that we did in polar. Maybe I didn't mention this in the cylindrical section, but you would do sort of a similar trick. If you get a negative distance specified, assume that you go in the opposite direction of whatever angle you're discussing, okay? So if we got a negative k, specifying, pretty much open range, any angles allowed, we would get a sphere back of radius k, okay, if there are no restrictions, okay, on phi or theta. Okay, and then the one special case that's an exception to this, special case If k is equal to 0, this is just going to be the single point at the origin. Okay, so that's the one exception to this that's not going to give you a sphere back. What about my other variables? Well, theta, if I'm worried about what's going on with theta, well, let's think about this. Okay, theta is supposed to be, if I have some sort of a, shadow point in the xy plane for whatever location that I'm specifying, how we get this measurement theta is you would go ahead and connect a line from the origin to this point, and that would give you, whatever your theta is back. Now, notice, if I fix that as my theta, well, if I'm not specifying, any sort of other restriction here, so obviously I'm making a note here, k a constant. Let's go ahead and assume no restrictions similarly on, let's say, rho or phi. If there are no restrictions on rho, this means that I can go as far out from the origin as I desire with this point. And if I'm allowing myself negative rho, well, like we said, whenever you get negative rho, you just go backwards from the angle that you're specifying. So we would end up going in the opposite direction. Now, if I don't specify anything for phi, well, what that means is we could, kind of come down along this angle at, any angle off of the z-axis that we would, desire to come down off of the z-axis. And the consequence that that's going to give us is, well, we're actually going to end up with a plane here, right? We end up with a plane, we'll pretend that was a straight line, that cuts through at this angle off of the positive x-axis. If I assume that this plane extends down below, we can do that. You just have to have a phi that is greater than pi over 2. But if I give you no restrictions on these points, we basically get a plane through the z-axis, okay, that is basically theta off from your positive x-axis, okay? And then the final case, we've investigated 2 of the variables already. What about the third one? This phi that I'm looking at. Okay, so again, if I specify k some sort of constant, what this phi was supposed to tell me is angle off of the positive z-axis, right? Now, if I specify some sort of an angle, phi here, anything that is phi off of the z-axis works. Now, the catch is, here I've kind of specified, with this line segment that I'm using to measure this, I'm kind of implying some sort of theta that corresponds to that line segment, but, similar conditions, if there are no restrictions on rho or on theta, I could go over to some other, angle theta and still take this measurement down off of the z-axis and get basically the same angle measurement. Now, I can do this all the way around. So, go to each of the angles theta off from the positive x-axis, take that measurement, dropped down from the z-axis. What we'll basically get is a cone. And if I have no restrictions on what's going on with rho, remember we said going in the opposite direction whenever your distance ends up being negative, if you have no restrictions on rho, if you allow negative values, you also get the cone that's on the bottom here that mirrors this as well. Okay, so if there's no restrictions there, you get a cone that is going to be basically whatever angle this is off of your z-axis. The one special case that I would mention that you have to worry about, this is going to be the case assuming that you don't get this one particular angle. If you don't get, actually, two angles would potentially cause this. Actually, maybe three. So if you don't get 0, if you don't get pi over 2, this is another special case. If you don't get pi, those are kind of the weird ones, because most cases you're going to get a cone here. I will go ahead and mention these other special cases. If your phi ends up being 0 or pi, well, if you are 0 radians off of the positive z-axis, you basically have to be on the z-axis. We've mentioned that if you're not restricting rho, you can also go in the opposite direction. You're basically going to get the z-axis, okay? Similar argument for if you choose phi is pi. The other special case that you maybe have to worry about is if you end up with pi over 2. Well, if I'm thinking about that guy here, well, the locations where I'm pi over 2 radians off of the z-axis basically are going to put me on the xy plane. Okay, so these are the two non-cone cases. I'm going to get my xy plane back. Okay, so these are kind of the surfaces that we run into, and this is why earlier I said that we probably want to think about intersections of spheres and cones, because these constant surfaces give us spheres and cones back. We can express these things with constant bounds. Now, that's all well and good with the picture. How do I do this algebraically? There are some algebraic conversions to spherical. If you're wondering, how do I rewrite x? How do I rewrite y? How do I rewrite z? These are going to be our trick for rewriting x, y, and z. Now, if you're wondering where these come from, I'm not going to bore you guys with the details. I will go ahead and make the observation that we're really doing pretty similar work to what we did in the cylindrical section. You know, why do I have all these trig things floating around? This basically works by SOHCAHTOA. If you want to draw the diagram and kind of grind it out, all we're analyzing is a bunch of right triangles here. So, you know, if you represent, you know, whatever triangles you need with respect to, you know, the point that you're drawing in space, this is how we're grinding each of these out. Okay, and I'm not necessarily going to bother you guys with the details. Just, you can either trust me that it works, or if you're bored, you can check it yourself. This last equation here, this is kind of a shortcut. Very similar to cylindrical, we do get a shortcut. In cylindrical coordinates, we got that x squared plus y squared we could rewrite as r squared, and we also got that for polar coordinates too. Here, we're not really measuring an r distance anywhere though. Okay, spherical coordinates don't have an r, they have a rho. And if you're wondering how to get the rho back, well, kind of a similar trick. X squared plus y squared plus z squared comes out to rho. If you're wondering where this comes from, you know, you can check that this guy works either by your sphere equation or by your distance equation. Okay, your distance formula. Okay. Now, if you're wondering, now that I've got these conversions, you know, if I give you a Cartesian coordinate, yeah, like I did a couple examples ago, you know, we wouldn't have to worry about drawing the picture. I could actually get the point back, just shoving stuff into formulas. But it's all well and good knowing how to convert points. How do we convert integrals to my new coordinate system? Well, told you guys to get used to me saying this for the rest of the semester. If I'm worried about converting an integral, a triple integral to spherical, there are 3 things that I have to fix. So the things that I'm worried about fixing are, we are going to have to fix my bounds. I will hope that they are expressible in terms of constant bounds and spherical coordinates. I will need to fix my function. Okay, so the reason that I gave you the x, y, and z above is so we can replace that in my integrand. And I have to fix my differential. Okay, so these are my 3 things that I will need to fix to rewrite my integral. Now, if you want kind of instructions more detailed on how to do that, well, I got them right here. My integral conversion steps are going to involve me fixing, again, my bounds, my function, and my differential. Okay, so if I needed to convert my bounds, I keep telling you guys this, there's really not a handy dandy trick to swap your bounds directly over to a different coordinate system. You are going to have to develop some sort of spatial reasoning for what that region looks like. So I would highly suggest trying to sketch it to figure out what it looks like, what surfaces you have, or if you're given equations, be able to recognize the equation for a sphere or a cone when you see it. That'll help you figure out what these bounds on rho, theta, and phi look like. The second thing that I'll need to do is go ahead and fix whatever function that I am looking at. Now, this is exactly why I gave you those conversion formulas for x, y, and z, and also for the instance that you see it for x squared plus y squared plus z squared. If you have a function that you are trying to integrate and you see an x, you can replace it with the formula. If you see a function and it's got a y, you can replace it with the formula that I just gave you. Same deal for if you see z. And a comment that I'm going to go ahead and make, if you do see x squared plus y squared plus z squared and you try the first 3 formulas instead of the last one, there's nothing technically wrong with that. But you're just going to have to apply some trig identities to do some simplifications. You will get the exact same thing. Okay, so any of those, 3 formulas above or 4 formulas above will be relevant for helping you fix your function. A comment that I will make, though, that ties back to bounds, whenever you look at your bounds, please don't try to fix your bounds using those techniques. It's probably going to be a lot cleaner if you just figure out what your region looks like instead. And then the final thing that I'll mention before we move on, the last thing we have to fix in the integral is the differential. We have to replace that dv with rho squared sine phi d rho d theta d phi. Okay, so kind of what's going on here. I won't bore you guys with the derivation of this. I will go ahead and note this is kind of like polar or cylindrical in that we need a conversion factor, right? We need a conversion factor. In our triple integral, when we go to, let me spell that correctly, factor. When we go to rewrite a triple integral, we're trying to replace dv. V stands for volume. Hopefully, if you think about it, multiplying your distance to the origin by 2 angles isn't necessarily going to directly give you a volume back. So you shouldn't expect that d rho d theta d phi automatically equals dv. It doesn't. That's not how you compute a volume differential. Okay, so the factor that we have to convert by to compensate for that, it's going to be this term. So any integral that you're looking to rewrite, either if you have a dv integral or a dy dz dx or dz dx, whatever, if you have those differentials in some order and they're directly equal to dv, you can make this replacement. Okay, so let's see if we can actually try this with a couple examples here. I will have us start off small, find the volume of a sphere, radius r naught. So basically derive the sphere volume formula. Okay, well, if I'm trying to find the volume of this sphere of radius r, or r naught, what's volume, right? Well, if this sphere is my region, I'll call this E, what's volume of E? Well, I've told you guys, if you're worried about volume, your volume should always be basically what happens if you integrate one with respect to volume over that region. Okay, so the trick in most of the integrals we are going to run across is if you want to measure something, integrate one with respect to the appropriate differential. This is what we need to rewrite. Okay, so here, if I'm worried about fixing my bounds, how do I fix my bounds? How do I represent E? I've got three variables that I'm concerned with here. What's going on with rho? What is going on with theta? And what is going on with phi? Rho is distance from the origin. Now, if I'm including the volume of the entire sphere and all of the points that are inside of it, that means that I'm, starting at the origin, that's 0 units away from the origin, and the furthest away outward that I could go is going to be r0, because this is my sphere radius r0. The next bound that I am worried about is theta. What is theta? Well, if you're worried about theta, kind of a way to picture this here is if you try to, this is a terrible arrow, but if you try to think about what's going on in the XY plane for your region, theta is just where do we go, around, this, around the origin, where are all the points in my region? Now, sometimes we go all the way around. This is exactly what we're doing here. The sphere does go all the way around the origin in this sense. But if you were restricted to some quadrants and not others, this is where you would specify that range. Like anything in the first quadrant would just be between 0 and pi over 2. If you were in the first two quadrants, it would be between 0 and pi, and so on. Here, since we do go all the way around, my theta is stuck between 0 and 2 pi. And then finally, what I want to ask myself is, where is my phi? Well, my phi is going to specify what sort of angles am I allowing myself to travel off of the positive z-axis, and, unless I want to double count points, starting on the z-axis, and there are points inside the sphere there, starting on the z-axis, we're at an angle of 0. And then the furthest we can travel down without double counting points and lapping back around is you can go pi units down. So these are going to be our bounds for E. It's a sphere, but it's expressible entirely in constant bounds for us. Now, the integrand, fixing the integrand, okay, if I want to fix my function, I said anytime that you see x, y, or z, you have to replace them. In this case, this is a pretty simple example for spherical. There is no x, y, or z to replace. And if you do not see an x, y, or z to replace, your function stays the same. Okay? Stays the exact same. Final thing that I need to do is replace my differential. Well, we said before that my differential, okay, we can go ahead and look back at this one more time, because I know the formulas are new. The conversion that we said was rho squared sine phi, d rho d theta d phi. So that's what we need to use here, okay? So dv is going to be rho squared sine phi d rho d theta d phi. So this will let me go ahead and rewrite my integral, okay? I'm going to go ahead and get my function straight. Okay, my function was just 1, no change. My differential that I had to tack on to the end and replace dv with was rho squared sine phi d rho d theta d phi. And now I just have to make sure to match up my bounds appropriately. We said rho is stuck between 0 and r0. Theta is stuck between 0 and 2 pi, and phi is stuck between 0 and pi. Okay? Now, if I want to go ahead and actually evaluate this, I will make kind of a side note here. We can evaluate this thing directly, or you can go ahead and split up your integral if it looks like a product of a function of rho and a product of a function of theta and a product of a function of phi. Okay, so if this looks like a product of a function of rho, of theta, and of phi. Now, we did a very similar trick to this in the double integral section. You can do a similar trick to this in the triple integral section. It still holds. Kind of the idea is this. As an example, first thing that I would do if I was evaluating this inner integral directly is I would have to integrate with respect to rho. That means phi, and thus sine phi, acts like a constant. If you wanted to, you could pull that out of this particular integral. That would leave your inner integral as just being 1 of rho squared with respect to rho, but you know, once you evaluate that whole thing out, you get a constant. That means you could pull that whole integral out, and if we do that, you know, just your rho, well, we're left with this guy. And that means that you are left with a, you know, 1 times sine phi here. If we did a similar trick, you could also pull out a integral of 1 with respect to theta. And finally, the last thing that you're left with here is the sine phi that we are integrating from 0 to pi. Now, you can use this trick if you've got a product of, you know, functions of rho and theta and phi, or if you want to evaluate directly, or if your functions are not expressible as a product, you can evaluate directly. But I'm just showing you guys this trick because sometimes it's helpful. If I do apply this trick, I've now got 3 single variable integrals, so this is basically 3 calculus 1, calculus 2 problems. I will get, you know, rho cubed over 3, evaluated between 0 and r naught. This needs to be multiplied by theta, evaluated between 0 and 2 pi. That needs to be multiplied by minus cosine of phi, evaluated between 0 and pi. And if I go to crank each of these guys out, I've basically got r naught cubed over 3 times 2 pi, okay, because I'm subtracting off 0 in both of those cases. Here I would have minus cosine of pi. Cosine of pi is -1, and then I would need to subtract a minus, well, that means add. We need to add cosine of 0. Cosine of 0 is 1. So, I basically got r cubed over 3 times 2 pi times 2. So, I'll get 4 pi r naught cubed over 3. And this actually does coincide with my volume of a sphere formula. Okay? Now you've seen that, let's see if I can maybe give you guys some trickier ones. For example, we'll try this guy, where I actually do have a function that I have to screw around with. Let's evaluate this, where we've got the region above the cone, z equals root x squared plus y squared, and below this sphere, okay, that I give you guys. Now, 3 things to fix. One of the first things I want to fix is my bounds. That means getting a feel for my region. I say that we're above a cone. I've drawn this for you guys a number of times. This is basically the cone that is 45 degrees off of the z-axis. Okay, so perfectly even here. And then, if it's above the cone and below the sphere, well, I'm basically looking at the snow cone kind of thing right here. Okay, so ignore the rest of the sphere, ignore the rest of the cone. We're just focused on this bit that's positive. Now, if I wanted to figure out my bounds, using what I have just noted, again, the 3 things that I need to worry about are rho, theta, and phi. Well, I just told you guys that that cone is only allowing us, well, I'm not even worried about the cone now. Probably the distance from the origin is the first concern. Rho is my distance from the origin. We do have points that are on the origin, so 0 is a lower bound. If I'm worried about how far out I can go, well, that's going to be limited by the sphere. What radius is my sphere? Please don't forget this is an r squared on the end here. The radius of that sphere is 2, not 4. Okay, so that'll sort out my rho. If I'm worried about my theta, again, if you think about what's going on in the xy plane, you know, where is your region here? In this particular case, we do go all the way around, so kind of like last time, still stuck between 0 and 2 pi. If you do not include points that go all the way around, you'll get a different set of intervals there. And then the final thing that I mentioned, this is where we have to take into account the cone. Phi is going to give you your angle off of the positive z-axis. Okay, we do have points on the z-axis. That means that we do have points with 0 as a lower bound. But I told you guys this is the cone that only comes 45 degrees down. So if this is the cone that only comes 45 degrees down, my upper bound on phi is pi over 4. That will let me fix my bounds. If I'm worried about fixing my function, well, here I'll go ahead and make that note. My function is basically going to turn into, you can plug in x and y and z and simplify, or use the shortcut. You know, x squared plus y squared plus z squared is rho squared. I can replace that function in the integrand with rho cubed. And then go ahead and do note we will have to fix that differential at the end, okay, with rho squared sine phi d rho d theta d phi. Okay, so this integral now, we're now integrating a rho cubed. We do still have to fix my differential d rho d theta d phi, and then I have to set things down in terms of the order that I just gave. So rho, theta, and phi. And I can go ahead and simplify this and apply the same exact integral split up technique that I did before. I'll look at my rows first. Okay, my rows have bounds 0 to 2. If I simplify those, I end up with something to the 5th. My thetas, I don't really have a theta in here, so I'll go ahead and assume that there I'm just integrating a 1. You know, we can throw a 1 in here. It's all the same. And then my phi function that I can tack on the end here, we still have a sine phi. So here's my 0 and pi over 4. If I actually take care of all of these are, you know, single variable integrals, pretty standard work. I get a rho to the 6th over 6, evaluated between 0 and 2. I will get a theta evaluated between 0 and 2 pi, and I will get a minus cosine phi that is evaluated between 0 and pi over 4. So here, let's see what I get. That's 64 over 6 minus 0 times 2 pi minus 0. Here I've basically got minus root 2 over 2 minus a negative 1. Okay, so you know, I'll worry not about this simplification here. Hopefully you guys get the point of the integration. And we'll try to squeeze in one more example here. I know we're running pretty close to what would be usual class time. I mentioned that we're doing these to be able to convert triple integrals. Sometimes I might express that triple integral in terms of how I would usually, you know, actually set up a triple integral. I could give you dz, dy, dx, or one of the other combinations with actual bounds on those. The trick that I would suggest for tackling one of these, I said there is no direct way necessarily to get my bounds back. Please try to figure out what it looks like if you sketch your region first, right? That's probably what I would suggest. And a comment that I'm going to go ahead and make here. Note number 1, if I've got my bounds on Z, okay, being stuck between Z equals 0 to Z equals this awkward square root thing, we've hopefully seen these square root type problems enough to recognize that this guy right here, this thing really looks like if you rearrange this and solve for, you know, your constant here, you can rearrange this into a circle equation, right? So this is basically the upper half of that circle, or sorry, sphere. So if we've got basically Z equals 0 to that sphere, the surfaces at least that we're dealing with are, you know, hemispherical. But I do have to pay careful attention to what's going on with the rest of my bounds, right? Like, for example, I've mentioned that y has to be stuck between, you know, 0 and 9 minus x squared. Okay, so, you know, y equals 0 to y equals root 9 minus x squared. Similar comments here. You guys have hopefully dealt with circles and spheres enough that we can recognize that this thing looks like the upper half of a circle. So if I wanted to think about, you know, just strictly my xy plane, y equals 0 to that curve is really specifying this curve with my xy plane. And what that's going to mean is that I don't actually care about the whole hemisphere. I just care about a portion of it, and which portion, last bound that we need to take into account is that x is stuck between 0 and 3. That means we don't even care about the whole half circle, right? You know, if I'm going from x equals 0 to x equals 3, I'm just worried about this bit that is above the first quadrant, okay? So just that section here. Okay, I may as well disregard the stuff in the back. We are basically looking at the first quadrant. Okay? So, if I want my bounds on that, well, again, rho, theta, phi. Rho is supposed to be my distance out from the origin, and you'll notice, you know, my circle that I'm dealing with, my sphere that I'm dealing with, those both have radius 3. So if I'm going with all my points from the origin all the way out, that's my bounds on rho. If I'm worried about my bounds on theta, well, we just talked about what was going on in the xy plane. This is only going to concern us if we're between 0 and pi over 2. And if I'm worried about phi, phi is going to tell me how far down off of the positive z-axis I am coming. This very similarly, I kind of hit a flat line here at this xy plane. I'm stuck between 0 and pi over 2. So, if I wanted to rewrite this integral, okay, the integral that we had, my function is just x. I'm going to have to rewrite x, and then I'm going to have to rewrite my differential. I'll go ahead and do that in line with my integral here. If I rewrite x, well, x I told you guys was this expression. If I rewrite my differential, right, so I'll go ahead and note this was us rewriting x. If I rewrite my differential, well, dz, dy, dx, or dv, whatever, we've said that we're still supposed to use rho squared sine phi d rho d theta d phi. And then that sets up the order that I needed to match my bounds up with. Okay? So if I wanted to clean this up a little bit here, okay, I can. You know, my row integral, you know, if I match up all of my rows, put those together, we've really got 3 of those here. If I wanted to match up my thetas, I can do the same trick that I did before. There are no thetas, actually, let me get my, oh, so this was me messing up with my handwriting here. This should be a cosine theta, not a cosine phi. Sorry about that. So I do actually have a non-trivial theta integral to pull off here. Here's my theta integral. And then for my phi integral, you'll notice I've got a sine theta, or sorry, a sine phi and a sine phi. So that'll be my last piece there. So sine squared phi d phi. Okay. Now I'll go ahead and you know, just make a comment about solution for these guys. You know, the beginning of these are pretty straightforward. You know, power rule. You know, we've anti-derived these trig functions a couple times thus far, so this isn't anything crazy. This last guy, though, it might have been a while since we've seen this. A comment that I'll make about this unit, since we are dealing with a lot of trig functions, sometimes you will have to dust off those trig techniques that we did back in Calculus 2, so things like using U substitution, using half-angle identities. So here, this would probably be a good technique. Okay, cosine 2 phi over 2. Those techniques are going to be techniques that you probably want to dust off for this unit to be able to tackle some of these integrals here. Okay, so I'll go ahead and note this is basically our half angle trick from Calculus 2. Okay, and since I mostly was worried about setup here and, you know, pointing out that technique, I don't really want this video to drone on too much longer. You know, if you're not interested in the full-on answer, you're welcome to tune out after this, but if you don't mind the extra, like, minute or two that it takes, we can go ahead and wrap this up. If I want a full-on evaluation for this thing, basically got 81 over 4 for this piece. Sine of pi over 2 is 1, minus sine of 0 is 0. If I'm going to anti-derive this piece, I've got 1/2 phi minus sine of 2 phi over 4, evaluated between 0 and pi over 2. Okay, and then final evaluation here. If I plug in the pi over 2, basically got a pi for this piece. If I plug in the pi over 2 here, well, I've basically got a sine of pi to worry about. That's 0. That means that I can now worry about what happens when I substitute in 0 for both of these, and for both of these I get 0. Okay? End result, 81 over 4 times pi.